Good morning. Happy to see so many people despite the fact that this is the day between Ascension Day yesterday and the weekend. So the topic of today will be a brief cap or recap of liveness, but in particular the main focus will be on fairness properties. So what you have seen in the previous lectures were linear time properties. And what we have seen in the previous lectures is that actually the whole spectrum, so the entire universe of linear time properties, if I would draw a Venn diagram of this, then this would be the whole set of LT properties, right? So this is the set of LT properties. This is this thing. Then actually we can subdivide this entire universe in a couple of, we can actually partition this. First of all, we have seen that we have a couple of properties that we call safety properties. Yeah. Safety properties are those properties that if you want to show that they don't hold, so in order to show that they are refuted or violated, a finite prefix is sufficient. This is what we call the bad prefix. Then there are properties, for instance, this includes invariants. Yeah, so if you would take from this, and these are probably the invariants. These are part of the safety properties. Good. What else? Well, in the last lecture, Chris introduced you to liveness properties, and I will just briefly recap this. So these are liveness properties. Let's put them here. And this is almost the truth, because there's one property which is both a safety property and a liveness property, which is the property true. So here is one single property, which is both a safety property and a liveness property, and this is the property true. Yeah, in terms of a logical formula or in terms of the set of traces, this is the entire universe. So this is 2 to the AP omega. Yeah? Basically all infinite traces over a certain set of atomic propositions. Good. And then the question is, what is here? Yeah, and this was the result that you have seen in the last lecture. This is what is the decomposition theorem. And this is a very nice, elegant result that actually tells you any property which is there, right, which is neither a safety nor a liveness property, is equivalent to a conjunction of a safety property and a liveness property. Yeah, so any property here, for any property, and I'm talking about LT properties, so sets of infinite traces, right? These are the kind of properties we talk about. For any LT property P, that in question mark, we have, there exists a property Q, such that P is equivalent to Q, and Q is simply the conjunction of a safety property and a liveness property. Yeah, so you can always, let's say, take the property and break it into two parts. One that tells something about liveness. And remember, in liveness properties, you don't have this nice property for safety properties that a bad prefix is sufficient to show that it is refuted. No, a liveness property actually allows any finite prefix, but only tells you something about the infinite behavior. Something needs to be true infinitely often, something needs to be true eventually at some point in the future. But it's always the case that you can, let's say, take a property and decompose it. And of course you may argue this also of course holds here. The liveness part is there empty, and here this is always also true because here the safety part is empty, right? So you can even see this as a kind of, let's say, result that applies to any LT property.
By LT you mean the whole set?
The whole set. Yeah. You take the conjunction with something which is true, so which is actually exactly this property which is here in the middle. Yeah. Empty is maybe not the right wording. Yes. Good. Okay. So now you may argue, well, we're done, right? We have seen the entire spectrum of LT properties. We know what are LT properties. We know what are safety and liveness. And today we're going to talk most of the time about fairness. Yeah. So fairness is something that we're going to see is going to be important for liveness properties, or for properties that partially are liveness properties, so the question mark and those things. Yeah. And I'm going to introduce why fairness is important, what type of fairness are existing. So basically the most important thing is that we're going to talk about this part, basically. Yeah. And we're going to show that fairness assumptions, as they are called, so mind, these are not LT properties, right? These are assumptions, and I'm going to make precise what that means, right? But those assumptions are going to be relevant, and this will be a result completely at the end of the lecture, for the dashed area. In particular, we're going to show a result that tells you that certain fairness assumptions, a very mild restriction of it, is not affecting the truth of a safety property. Good. Okay, that's already something that we're going to see in more detail in this lecture. So, just I think I'll quickly go over here. Liveness, Leslie Lamport in the 70s tried to give a colloquial definition of what liveness is, and he said something good will happen eventually. So event A will occur eventually, for instance, termination. Event A will occur infinitely many times, and whenever event B occurs, then event A will occur sometimes in the future. The crucial point is, and that's the best intuition I can give you, a refutation of a liveness property can never be given by a finite prefix. Yeah? I mean, take for instance the last property, whenever event B occurs, then event A will occur sometimes in the future. Now, you can argue, okay, I'll give you a bad prefix, right? What would be the bad prefix B? Well, the bad prefix has to be finite, so at some point we have a B, and we don't see any A. Yeah? Suppose this is the finite bad prefix. Yeah, that would be your proposal. Hey, show you property is violated. And then I'm arguing no. Why not? Yeah, because it could be the case that this A occurs somewhere here, right? Later, after your prefix. And then it fulfills this property. Or maybe this A occurs there. Yeah, so it's never sufficient to get a finite prefix. And that's the intuitive way of understanding what is a liveness property. So therefore, this is not a bad prefix. Good. So important, and I think this will also be one of the things that you will be confronted with in the exercise series, is which are the property types. I already gave you this intuition. Safety properties have a finite bad prefix. Liveness properties don't have such a thing. So if you think something like each philosopher thinks infinitely often, the fact infinitely often should make clear that a finite prefix doesn't exist, so this by definition is a liveness property. Two philosophers next to each other eat at the same time. This is something you can provide me a counterexample by means of a finite prefix, and you gave me a finite prefix where this is not true. Yeah? So this is an invariant, and that's a safety property. And there are several others, like a safety, aliveness. Whenever a philosopher eats, then he will think sometimes afterwards. This sometimes afterwards is similar as this example here. Whenever a philosopher eats, B, then he will think, A, eventually. That's exactly the same scenario as we just have seen. Good. So there are, actually, if you look at the literature, there are many formal definitions of liveness properties. And what we take is actually what they call the Alpen-Snyder characterization. And if you are familiar with topology and mathematics, then actually the mathematical characterization is basically that safety properties are closed sets in a topology, and the liveness properties are the open sets. Yeah, and that's, I mean, I don't want to give a lecture here on topology. This would be outside the scope of this lecture, but that is actually the main reason why we look at this definition, and not at one of the other, I don't know how many in the literature. So the definition you have seen in the previous lecture is that you are given an LT property, which means this is a set of traces over a set of atomic propositions, and E is called a liveness property if each finite word over the current alphabet, which is AP, can be extended to an infinite word satisfying E. Each finite word, this one, can be extended in some way, for instance like this, such that it satisfies the property. So already by definition, a counterexample, a finite counterexample cannot exist. Because by definition, a liveness property says that every finite word can be extended. And that means actually that if you look at the set of finite prefixes of such a set, which are the finite prefixes of all its elements, are just all finite non-empty words over the alphabet. Good, and we have seen already quite some examples. So here is an example that of a critical section. Each process will eventually enter its critical section, is something which is typically a liveness property, and again this is eventually. If you give me a finite prefix, the process has never been in the critical section in the finite prefix, you can always extend it by adding one action or one state in which has just entered the critical section. So the way to formalize such a property is something like the set of all infinite words. Remember, those A's are sets of atomic propositions. And what do we have to require? Well, we have to require that actually eventually will enter the critical section for every process. So if there are n processes, you require for all n processes that there is some index in this sequence such that at position k in this sequence, process I is in the critical section. And because you require this for all processes, the universal quantification, then you have specified what is written down here. Each process will eventually enter its critical section. Each process will enter its critical section infinitely often. So it's not enough to go 100 times to enter the critical section. No, you have to do this infinitely often. And the way to write this down is something like this. Again, we have to characterize a set of the property, which is a set of traces, so it's a set of all infinite words. Again, we would like to say something for all processes, that's this first universal quantification. Then we want to say you enter the critical section infinitely often, and I use this existential quantification with this superscript infinity to say there are infinitely many k's that are at least 0. So intuitively speaking, there are infinitely many positions along this sequence such that at this position, process I is in the critical section. Good. You might think that these properties are a little bit cumbersome to write down in such a thing. Later, we will see that you can also describe these kind of properties conveniently in terms of a logic, which is linear temporal logic. So later we're going to use logics to describe what is here in this gray box in a much more succinct way. Whenever a process is waiting, then it will eventually enter the critical section. So one way to write this down, similar pattern as before, the set of all infinite words of this shape, such that a certain condition is fulfilled. Same as before, the outermost universal quantification is the quantification over all processes. Now, what we have to say is whenever a process starts waiting, then at some point later, or eventually, it will enter the critical section. So for all positions j along such a sequence of a trace, if at this position j process I starts waiting, then at some position later than j, process I is in the critical section. Yeah? Good. So for safety properties I already mentioned before, then actually it means that if you take a trace which is not in the safety property, that means if you give me something which violates the safety property, then there must be a bad prefix, and that's actually the case. Then there exists a finite prefix, A0 to AN, such that all its extensions are not satisfying the property. That means that the set of traces belonging to E, which are such that have as a common prefix this bad thing, is empty, which means there is no extension of this bad prefix. Good. This was the decomposition theorem. I already intuitively showed you this safe and live intersection. I think, Chris, you did the detailed proof on the blackboard, so I'm going to skip this part. Good. Okay, here this was already also what I mentioned. Which L2 properties are both a safety and a liveness property, and this is exactly this one single property over here, which is the property that actually is in logics you would write down true, because you don't restrict any behavior. In terms of a set, you take the set of all possible infinite traces, and it's 2 to the power AP omega. Good. Why is this a liveness property? Well, because you don't rule out any prefix. So therefore the closure is 2 to the power AP omega. That was another description of being a liveness property, namely that the closure of the set of traces you are considering is the entire universe of traces. That's the other way of writing down a liveness property. And it's a safety property too, because then the closure of E is E. So that means the closure of E is this set, which is exactly the set we started with. So therefore it's a safety property. This was the property we had for safety properties, that if something is a safety property, so if E is a safety property, then the closure of E equals E itself. Good. Now I get to the introduction to these fairness assumptions. As I mentioned already, they will be relevant for this part, for the liveness property, and for properties that are partially liveness. And what's the main underlying reason? The main underlying reason is that liveness properties are often violated, although we expect them to hold. And I will give you some examples that I will then hopefully basically will give you some intuition that we maybe want to do something about this. And this doing something about this means that we're going to introduce fairness assumptions. So this was an example we have seen earlier. We have two independent, very simple traffic lights. Very simple means they only have two states, green or red, and they run in parallel. Running in parallel means that if you take the interleaving of the two traffic lights, this will be the usual Cartesian product of their state space. Now, this parallel composition of the two traffic lights does not satisfy the property infinitely often green 1. Why not? Well, you can start here. Well, that's the only option to start, so we should start here. Then we could, for instance, go here, right? And then we go back. We go here, and we go back. We go here, and we go back. This is a possible behavior, right? Actually, the green light will never become green then. What does that mean? It means that we have two processes, light 1 and light 2. Light 2 is moving down and moving up, moving down and moving up, so it's evolving. But the first traffic light is basically starving. Now, this is not something that you would intuitively expect if you give me two threads. Both are enabled all the time. Only one of them gets its turn. So the question that you may pose, is this fair? Is this fair with respect to this poor process light 1 that is enabled all of the time but never gets its turn? Yeah? Well, maybe we think no. So what I want to say is that this liveness property, right, is violated because there is some kind of behavior that maybe is not exactly fair. And maybe we want to get rid of this unfair behavior. Maybe we don't like the fact that only 2 is doing something and 1 is starving. And this is exactly where fairness assumptions come into the play. So intuitively speaking, by means of fairness assumptions, we're going to rule out, we're going to eliminate certain behaviors that are not fair. And now the question will be, what does it mean to be not fair? And we're not going to talk about politics. I think there are many flavors of being not fair. But also in terms of those behaviors here, you may argue, what is fair? Is it fair maybe that this one does infinitely often this cycle and that one does this 100 times? But not 101 times? Not 1 million times? Not infinitely often? Is that fair or is that not fair? Well, maybe it's a matter of taste. Yeah, so what we're going to see actually, there is not a unique notion of fairness. Yeah? I mean, there's one definition of a safety property, there's one definition of a liveness property. Okay, there are many equivalent ones. But for fairness, there's also a matter of what kind of behaviors are we going to rule out. And what we're going to see, I'm going to give you 3 possibilities here. But there are many more, actually. Good, so this is the effect that we only cycle in between those 2 gray states, and actually the first light will never get its turn. And this is the point. The light itself, right, satisfies infinitely often green. I mean, this one, if you ask me, does this light satisfy the property infinitely often green 1, you would argue yes. Yeah? But then, put in a context with another process, it is not interacting at all with the other process, and then by accident there's a possibility that it gets starved. Yeah? Good. A way to write this down is we look at interleaving. This is the interleaving view on the parallel execution of the 2 traffic lights. And there is not notion of a fairness that's completely abstract in that sense. Good. Another example. So a second example to motivate why we need fairness. This is the transition. This is the model where we used 2 processes. And we use a semaphore, a binary semaphore Y, to get access to control the access to the critical section. And this was the transition system we have seen before. Now look at the following liveness property. Why a liveness property? Remember, I'm always talking about this set of properties, right? We're going to see completely at the end that we can prove that fairness is not playing any role for safety. Yeah? So I'm always starting with a liveness property. So, liveness property this, each waiting process will eventually enter the critical section. Sounds like a reasonable property, right? You start waiting, and then you would like to be able to get access at some point to the critical section. This is not satisfied by this process, or by this transition system. Yeah? So this transition system violates this property. Although the property looks very reasonable, it's actually maybe something that you may even expect. Because if you look at the 2 individual threads, then infinitely often, I mean, they at some point start waiting, and then they will eventually get access to the critical section. Otherwise, they can't progress. But in context, again, 2 threads, this is no longer the case. So what's a possible behavior? A possible behavior is indicated like this cycle. We always look at, to show that something is not fair, you always look at infinite behaviors. Why? Because we only, as we're going to see, fairness will have an impact on liveness. Liveness means infinity. Yeah? So we look at an infinite behavior, which in this is this cycle. Now, here we see that process 2 starts waiting. Process 1 is in a non-critical section. It also starts waiting. So now both processes are competing to enter the critical section, but in this behavior, we go to the left. And that means that process 1 enters the critical section, process 2 is still waiting. Now it's possible that process 1 is releasing the critical section, that means it increases the binary semaphore by 1. We go back to this state, and again we go in this way. So what you see in this cycle, process 2 is waiting, but it will wait infinitely long. Yeah? It does not satisfy the property that eventually it will enter the critical section. Is this fair? You may ask yourself. Yeah? Well, maybe not. So each waiting process will eventually enter the critical section as a property that is violated, and that means that maybe, we should not allow these kind of loops. Here. Another example. So very similar procedure as of view as the two traffic lights running in parallel. Now they're called P1 and P2. They're just interleaved. What are the possible interleavings? If you look at the composed transition system, we know that states are pairs, S1 being part of P1, S2 being part of P2. And there are possibilities to do certain actions of P1, and there are possibilities to do actions of P2. Now, what are the possible interleavings? Well, we could say, but first P1 can do a move, then P2 can do twice a move, maybe then P1 can do 3 times a move, then P1 and P2 alternate, then 3 times P2, and so forth. Or here, there is a pattern that 2 times P1 and then P2 gets its turn. But this is also a possible, if you want, scheduling possibility, namely the scheduler, which is somewhere implicit in the model, says, well, P1 gets always the turn, but P2 is starving, similar to the traffic light, which never gets green. The two first things are maybe fair, because P1 and P2 in some way get their turn. Yeah? Whether they get an equal share of the turn, that's a different discussion, but let's assume those are fair, but I hope we agree that the third possibility is unfair. Yeah? So this has to do what people call process fairness. You assume that the resolution of the non-determinism, in such a state you have non-determinism because you can choose between actions of P1 and actions of P2. And in process fairness, you assume that there is an appropriate resolution, whatever that means. Yeah? Again, it's a matter of taste, what it means to be fair, what does it mean to be unfair. Good. So I mentioned already there are several notions of fairness, and we are going to concentrate on 3. Is this the whole universe of fairness? No. You can write an entire PhD thesis about the different flavors of fairness. I only, in this lecture, want to give you 3, I think, important fairness notions, but there are many more. Remember, fairness is to rule out the behaviors that are not fair, and the question is, which behaviors do you consider not fair, and which ones do you consider fair? So, one is called unconditional fairness, the other one is called strong fairness, and the third condition is called weak fairness. So intuitively speaking, unconditional fairness means every process every process gets its turn infinitely often. So in the previous process, like here, you may say, okay, these two threads are running in parallel. Let's assume P1 and P2 never get into a local deadlock. Then it's very reasonable that you say both of them have to get their turn infinitely often. So this would be an example of an unconditional fairness assumption. A strong fairness assumption says every process that is enabled infinitely often gets its turn infinitely often. So this does not unconditionally say you have to get your turn infinitely often. No, only if you only can do something infinitely often. Yeah. I hope you immediately see, without giving a formal definition yet, that if something is unconditional fair, it also is strong fair. Weak fair, every process that is continuously enabled from a certain time instance on gets its turn infinitely often. So what's the difference between the second bullet and the third bullet? Let me try to make that clear. Maybe by means of... Yeah, so maybe you look at the run of the system, and your run of the system is an infinite run. So here we have something like A0, A1, etc., A100, etc. Then the second condition, strong fairness, says every process that is enabled infinitely often gets its turn infinitely often. So if P1 is enabled infinitely often, it needs to get its turn infinitely often. So maybe here, this is an action of P1, this is maybe of P1, this is P2, etc., and this is maybe P1. Okay? And now you say if P1 is enabled infinitely often, what does that mean? It means that in every of those possibilities, P1 could do infinitely often an action. What does that mean? Maybe at certain points, like this fragment, P1 is not enabled. That's okay. Yeah. And maybe here P1 is enabled. And here P1 is not enabled. And here again P1 is enabled. And maybe we assume that, here again this pattern repeats, so here is not enabled, etc. Yeah. So what is important? There are infinitely often periods in which P1 is enabled. So here is good, enabled. Here is good, enabled. But there may also be certain amount of time, finite, in which P1 is not enabled. Good. This is strong. In weak, those periods that P1 is not enabled, there can only be finitely many of them. Or differently, weak means you have P1, P1, P2, P2, P1, etc. Right? And now from some point on, maybe from here, you have a period in which P1 is enabled continuously. And continuously means we don't have those fractions like here where this is not enabled. Yeah? This is not enabled, this is not enabled. Those periods are not present here. That's the difference between enabled infinitely often and continuously enabled. Good. How are we going to formalize this? We're going to formalize this by means of actions. So we're going to look at the actions that processes can execute. So what we're going to do, we're going to look at an infinite execution fragment. In this case, it's rho. An execution fragment, as you all know, it's an alternating sequence between states, doing an action, a state, an action, a state, an action, and so forth. And this is infinite. Okay? For the rest, I give you a set of actions, A, and we're going to define the notions of fairness with respect to this set of actions. So I'm going to provide you the formal definitions of unconditional fairness with respect to the actions in the set A of this run. The same for strong fairness with respect to A of the same run, and weak fairness of a run. Okay? So fairness is always defined, as my example showed you, on an infinite run. And we have those three different flavors. Important in the definition, it's parameterized by the set of actions we are considering. An action could be entering the critical section, start to wait for a critical section, releasing a critical section, and so forth. I'm going to use the following notations. Act of SI is the set of actions that you can take in SI. Right? So it's what I call the menu. There are those actions such that in SI you can take a transition labeled with this beta and move to some other state or the same state S prime. Then we use the notation that I already mentioned before. Existentially infinity, there exist infinitely many. And universally infinity for all but finitely many. Good. Rho is unconditionally A fair. What does that intuitively mean? I give you a set of actions. I'm going to say it's unconditionally A fair if actions in A occur infinitely often along the execution. So that means infinitely often some action alpha I will be taken. I mean, there are infinitely many alpha i's and they are in A. Yeah. So A is a set It maybe contains 10 elements. This only is saying there exist, right, infinitely many indexes along row. So infinitely many of those alphas that I will take are member of A. It is possible to always pick the same element of A. This is all fine. Yeah? If your set contains 10 elements, it's fine to always take the third element and do this infinitely often. That it will be unconditionally A-fair. Rho is strongly A-fair. What was the intuition? The intuition was strong fair means if you are enabled infinitely often, enabled now means if you can take an action in the set A infinitely often, then, yeah, you should do it. That means you should take such an action infinitely often. That's written down as follows. So the conclusion you see here is the same as with unconditional fairness. Yeah, so unconditional fairness simply can be written as true implies this formula. Now I change the premise by imposing this strong fairness. So if infinitely many states, yeah, the actions that I can take in a state along the run are member of A, yeah, that means the intersection of these things is non-empty, then I should take such an action in A infinitely often. Again, I take such an infinite run. I look at the indices along this run. This is saying there must be infinitely many indexes such that in state Si, I can take an action in A, then there are infinitely many indices where you should take an action in A. It's not saying that if always A, entering the critical section is enabled infinitely often, you should enter it infinitely often, because this simply says there is, yeah, this intersection is non-empty. In my actions, that was a set of 10, it could be the second one, which is enabled infinitely often. The conclusion tells only, take one of the 10, then infinitely often. It doesn't have to be number 2, right? It could be number 7. Yeah, this universal quantification is only on the premise, of this existential quantification, sorry, is only on the premise, this existential quantification is on the conclusion. Those two I's can potentially range over two different things. Weak fairness, yeah, sorry.
I'd like to ask for a counterexample for the strong fairness.
Sorry?
If I had traffic light that strongly switches from red to green and then doesn't do anything else, this in itself would not be fair at all, and also not in composition with other processes. Is that right?
Yeah, if it can only move from green to red, and that's all, yeah, it can do, then it's stuck. Yeah. So it stays red.
Yeah. And that's infinite behavior, but it's not fair at all.
Why is it infinite behavior? Well, it's a cycle on the red state. Okay. Yeah, okay.
But it can't go, okay. I was looking for a process that doesn't fulfill the initial condition of strong fairness.
I get plenty of examples. So if then it's still not clear, then please try. But your example in itself, I mean, first of all, you have to tell me which actions need to be fair. Yeah? Because the definition says it's always fair with respect to a set of actions. So that's the first thing you have to make clear. And then you can argue, is it unconditional fair, is it strong fair, or is it weak fair? Or maybe none of them. Yeah? Okay, so let's go to the weakly fair. Again, the conclusion is the same, but now the condition is that you should be able to do continuously. Remember, this at some point you should enable an action of A from some point on continuously. So that means, and that's the only difference, this existential quantification is changed into a universal quantification. It can be finitely often the case that some action in A is not enabled, but only finitely often. Yeah? And at some point, it's the case that from some point on, in all the states Si, you can do an action in A. That means the intersection is non-empty. Then you should take an action in A infinitely often. Again, this quantifier is only on the premise. This quantification is on the conclusion. So it's possible to have two different actions. One action which is continuously enabled in A, but it's possible to take infinitely often another action. This is all fine. So if from some moment on actions in A are enabled, then actions in A will be taken infinitely many times. Good. I hope it's clear that unconditional fair means only so strongly fair. The easiest way to see this is that right here true implies this formula. Yeah. Then it's clear that this implies this premise, and this implies that. So unconditional fair implies strong fair implies weakly fair. So one way to view this is the following diagram, but maybe it's useful. It's just written down as a Venn diagram, the same as what is written down here, but maybe it's useful. So I told you the aim of fairness assumptions is to eliminate unfair executions. Okay? So if you would make a diagram, there's a Venn diagram. This Venn diagram, this outermost circle, stands for all possible executions of a given transition system. This includes the fair ones and the unfair ones. It's all. Yeah. Now you impose a fairness condition. So one fairness condition could be something like a weak fairness condition. So now this is modeling this set. Yeah. All weakly A fair executions. So all executions that satisfy this condition, the bottom line. So what did we rule out? We ruled out all the behaviors, namely those. So here is maybe an execution. This execution is possible, but it's not weakly fair. So this is the behavior of which we, according to this notion, have said, this is not good, this is not fair. Good, then there is strong fair. And here is the set of all strongly, and of course I have to take the same set A, right? So A fair executions. So maybe to make this clear, I have to say that let A be a subset of the actions and fixed. Yeah. And then here, in somewhere here, there is all the unconditional. Yeah, so this is unconditional, strong, weak, all. Yeah. So with unconditional fair, you rule out more behaviors than by strong and by weak. Good. Okay. So here are two diagrams that a violation of strong fairness. So let's give an infinite run. This is the infinite run. The dashed lines mean, this dashed line means we take an action in the set A. This solid arrow means we take an action which is outside A. This means that we take an action which is outside A, but in this state there is an action in A enabled. We could have taken it in this run, but we didn't. This run took the other possibility. Here you see an option that, again, also here it would have been possible to take an action in A, but we didn't, at least not in this run, because we took another action that led us to state S7. In S7, a similar pattern. An action in A is enabled, and then we move to S8 and so forth. Good. What else do we see? We see this pattern of strong. We have patterns in which actions in A are not enabled, with periods in which actions in A are enabled. This is a period where an action in A is actually enabled and taken. Here is a period where this is enabled. Here is no outgoing arrow, no dashed outgoing arrow, meaning in that state it's not possible to take an action in A. So here is starting the period that A is not enabled. Again, here is not enabled. Here it is enabled. We didn't take it, but was still enabled. Here it's still enabled. So here is a period where A is enabled. The set capital A is enabled. Here A is not enabled. And here is again enabled. So you see that those periods, enabled, not enabled, there is not a continuous fragment there is always enabled, right? That's the important point. Now you see there is no A actions are executed from a certain moment on. You see that, for instance, here we see only the solid arrows, and assuming that the dot, dot, dot means that this pattern repeats. I don't take from some point on, namely from S2, I don't take any A actions. Yeah. And A actions are enabled infinitely many times. Strong fairness means if you can do an A action infinitely many times, you should do it. It doesn't, so therefore it's not fair. It's not strong fair with respect to capital set A. Maybe you don't like the set A. Well, then you should have taken a different set, right? Keep in mind it's parameterized in the set A. Weak fairness. So again, I have a run. Same as before, dashed means either you take an action in the capital set A or an action is enabled. Here you see a pattern that from this state on, you could always have taken an action in A. Some action in A. Maybe not always the same, but some action in A. But you didn't do that, right? Because from S2 on, you always are still having those solid lines, which means you don't take any A action from that point on. So that means that weak fairness is violated here, because from some point on, S5, there is a continuous enabledness of actions in A. All these states have this dashed outgoing arrow. But you only take A actions finitely often. In this example, only once. Good. I hope these two examples clarified the difference between strong and weak. Question?
So the first example would be weakly A fair?
You mean this example over here? Yeah, this is weakly A fair because assuming that this pattern repeats, there is no period in which A is continuously enabled. That means the premise is violated, and there it's vacuously weak fair. Okay? Good. So let's look at an example to make this more concrete. An example that you have seen already sometimes before. There are two transition systems. They both want to enter the critical section, and there is this arbiter, which is a kind of a semaphore that actually gives you access to the critical section by either synchronizing with the first process over enter 1 or synchronizing over enter 2 with the second process. And it can only synchronize with one at a time, and therefore only one of them can enter the critical section. This was the transition system we have seen before of the parallel composition of those three. Remember, I use the double bars here because we use synchronization here. I synchronize over all common actions. And this is the transition system we get. Good. So the question is unconditional, strong, or weak fair. Let's give some examples. Good. First of all, we fix a set of actions. In this example, I take a singleton set which only contains the action enter 1. Good. I look at an infinite behavior. This is exactly the behavior that we were arguing before that maybe it's not fair. The behavior where process 2 starts waiting, process 1 becomes waiting, process 1 enters the critical section, and we go back to this thing, and W2, you see, process 2 starves. Starves by it's waiting, but it never gets access to the critical section. Good. So this is the behavior in terms, the same behavior, but now written down as a finite sequence with this repetition here. And now you can check whether this is unconditional A fair, strongly A fair, or weakly A fair. So is this behavior, unconditionally A fair? Any opinions? Exactly. So here you see a transition enter 1, right? So you take this cycle, you take this infinitely often, so you take this action infinitely often. So therefore it's unconditionally A fair. then it's also strong A fair, and then it's also weak A fair. Yeah? Good. That's easy. Next action, different behavior. Same action set. This is the behavior. Okay? Question again, is this unconditional A fair? With respect to enter 1. So, in, let's say, spoken language, it simply means, do we execute action enter 1 infinitely often? In this behavior? No. We execute it 0 times. Good. So that's a no. Then the second, is it strong fair? Yes. Why is it strong fair? Good. In order to see this, we look at this behavior. Strong fairness says, if the action, enter 1, is enabled infinitely often, we should take it infinitely often. So the first question we should answer, is enter 1 enabled? Well, it's not enabled in this state. It's not enabled in that state. And it's not enabled in that state. How do I see this? You look at all the outgoing arrows of those 3 states, and none of them is labeled with enter 1. Right? So the premise doesn't hold. False implies everything. So that means it's strong fair. Then we're done, because if something is strong fair, it's also weak fair. Good. Different behavior. Now this is the behavior. It's the symmetric version of what we had before. Now we go to the left and then we go to this cycle. So now W1 is basically, process 1 wants to enter the critical section but never gets access. Question, is this unconditional A fair with respect to enter 1? Any opinions? Do we take enter 1 infinitely often? No. Is it strong fair with respect to enter 1? That means, is first of all enter 1 infinitely often enabled? Well, we take this cycle, there is at least one state in this cycle, namely this one, where you can do an enter 1. So enter 1 is enabled infinitely often. How many times do we take it? 0 times. So it's not strongly fair. Is it weak fair? Well, it's clear now, the answer is yes, but why is this the case? Again, yeah? Exactly. Exactly. Here you see enter is enabled, but then you move to this yellow state. There is no outgoing arrow here. There is no enter with enabledness. So there is no period from which on enter 1 can always be taken. Because every now and then, every time you go to the yellow state, it's not enabled. So that means the premise is false. False implies everything. Okay, same behavior as before. Now a little bit more complicated question. I now extended this set by having 2 actions. Enter 1 and enter 2. Okay, so we look at this behavior. Question, is this unconditional A fair? You say yes. You say no. That's nice. Why do you say no? Yes, but the definition says it's okay to take some action of A infinitely often. Some action of A. Yeah? We do this, we do enter 2 infinitely often. We don't do enter 1 infinitely often. Maybe you don't like this, that we not take enter 1 infinitely often, but then this means we are not imposing the right fairness assumption. If you think this is not fair, yeah? This is not the right fairness assumption to rule this behavior out. Yeah? So I'm trying to play a bit with this set to give you some feeling about how to get to this set that you are able to rule out the right behaviors. So this is unconditional fair, but if it's unconditional fair, it's also strong fair, it's also weak fair. So that's, again, easy. Good, I get more complicated version first. So actually what we have seen is, in general, you don't have only one fairness assumption, one set, and you would like to have it unconditional fair with respect to that set. But typically you have combinations. Some things need to be unconditional fair, some things need to be weak fair, and some things need to be strong fair. So what you need is a combination. And that's what we're formally going to define as being a fairness assumption. So fairness assumption is a combination, so if you like logic, conjunction of unconditional fairness assumptions, strong fairness assumptions, and weak fairness assumptions. Good, that sounds okay. But what are these calligraphic F symbols stand for? Well, they're actually sets of actions. Not just one set, but a whole set of sets. So that means that, and what's the intuition of this? So let's look at, suppose that we have F strong. And F strong is a set of actions, right? So maybe it's something of the form A1, A2, and A3. Then it means that it needs to be strongly A1 fair. It also needs to be strongly A2 fair. And it needs to be strongly A3 fair. Yeah? This could be something like, for instance, you need to be strongly fair with respect to enter 1. Maybe you need to be strong fair with respect to request 1 and request 2. I'm all referring to actions in the example of the mutual exclusion thing. And maybe you want to be strongly A3 fair with respect to, I don't know, enter 2. Yeah. And that means a run is strong fair with respect to this set. If it's strongly A1 fair plus strongly A2 fair plus strongly A3 fair. An execution, a run, is called F fair. So F is this triple. Every element in this triple is a set of actions. A run is fair with respect to this thing, to this object, if and only if it's unconditionally A fair for every A in this first set of actions. It needs to be strong A fair with respect to all A's in this set of sets. And it needs to be weak fair with respect to all actions in that set of sets. Okay, so it combines unconditional plus strong plus weak. But each of them themselves are combinations over several sets. Good. What is now a fair trace? What are the traces that remain after ruling out the unfair behaviors? The fair traces of a transition system T with respect to the fairness assumptions in this calligraphic F are defined as the set of traces of the trace of execution rho, such that rho is an F fair execution of the transition system we are considering. So these are the traces that remain after imposing all the fairness assumptions we are considering. Good. And this now tells you something about the fair satisfaction relation. And this is in this box over here. I give you a transition system, you give me an LT property. This is the property we would like to check. Remember, it's a property typically in these dashed areas because we're going to see fairness does not play a role for safety. Okay, so I give you a property, I give you a transition system. Then I define this new satisfaction relation. T is satisfying with respect to the fairness assumptions in F, property E, if and only if the set of fair traces of my transition system with respect to my fairness assumption are included in E. That means all the remaining traces, all the traces that are fair, yeah, these are here, they all satisfy the property of interest. Good example. Simple example, three-state transition system, two blue states labeled with the set of atomic propositions empty set, one green state labeled with the singleton set B. Two actions, alpha, beta. The action moving back to the initial state, I did not dare to give this a name. It's not so relevant here. Suppose I have as fairness assumption the following combination. Remember, a fairness assumption is always a triple. Here are the three elements of this triple. I say, wow, I don't have to impose any unconditional fairness assumption. I want to be strong fair with respect to the set alpha beta. So I have only one set. Remember, in general, we have a set of sets, but this is only a case where we have one set. And I don't impose a weak fairness assumption condition. So this gives rise formally to the following. We have this triple. The first component is saying the empty set because there are no unconditional fairness conditions. The second component is the set containing this set alpha beta, because I only have a singleton set here, or a set, one single set here. And there is no weak fairness condition. That means that the third component is also the empty set. Okay? Good. Suppose I would like to check, does my transition system satisfy the property infinitely often B? What does that mean? I'm interested in, can I visit the green state infinitely often? That's the question. Right? Now, if you don't impose any fairness assumption, is this true? Some people shake yes, some people shake no. This worries me a bit.
Well, I can visit the state labeled B infinitely often, but it's not guaranteed that I can.
So the question is there a trace of this transition system that violates the property infinitely often B, if I do not impose any fairness assumption? I mean, I could move here, right? I could go back. I could always cycle between the two Blaze states. I never visit the B state, so I definitely don't visit it infinitely often, right? Yeah. So I'm trying to look for some kind of fairness. Well, maybe you think it's not fair, because in the topmost blue states I can go left and I go right, and I always decide to go left. I always ignore to go right. Is this fair or not? Well, you may argue. Yeah? Good. The fairness assumption that we are considering is not the empty one, but it's the one where we are strong fair with respect to the set alpha beta. Now, what does that mean? If some action in the set alpha beta is infinitely often enabled, some action in the set alpha beta should be taken infinitely often. Question: is this true or is this false?
It's false.
False. Why?
Because whenever we're in the middle state, the top one of the actions, in fact both actions are enabled.
Yes.
This happens infinitely often.
Yes.
And always we have to take one of the actions. So
Yes.
the strong condition is fulfilled, but still we can do this while we choosing action alpha.
Exactly. Yeah. In this state, both are enabled. So I take the question is basically, do I rule out this behavior? We have seen this is the behavior violating that B, one of the behaviors that infinitely often B is violated. Well, you see that in this state, an action in alpha beta is enabled, actually both. But I always choose alpha, but that's perfectly okay. Because the condition says if some action in this set is enabled infinitely often, you should take some action in that set infinitely often. And I do this. I always take alpha. That means this property doesn't hold. Despite the fact that intuitively you might think, well, this should hold actually. Because in that state there's always an option to go to the right? So this apparently is not the right fairness assumption to rule out this behavior. No? So let's look at the difference thing. So that's what we just have seen. So now we are taking a little bit different. Again, no unconditional. We have weak fairness for beta and strong fairness for alpha. So formally speaking, this is the empty set. I did not even write it down. F of weak is a set containing only the set beta. And F strong is a set that contains only the set alpha. Okay, so intuitively, what does it mean? This thing has to fulfill the following conditions. If alpha is enabled infinitely often, I should take it infinitely often. The weak condition says if beta is enabled continuously from some point on, then it should be taken infinitely often. Okay? Question: is the property infinitely often be true or false? Any opinions? Still false. Yeah, does everybody see why? Yeah, because this beta and continuously enabled, I mean, you can still go here, right? In this state, beta is not enabled. So the precondition, beta is continuously enabled, is false. And that means the property is still not true, despite the fact that you think that maybe the property should hold, from a fairness point of view. So also this is not the right fairness assumption. And this is the behavior we just have seen. You take the cycle on the left, which means you always go to these blue states. Beta is infinitely often enabled, but not from some point on continuously enabled. Good. So does this solve the issue? Strong fairness for beta. That means if beta is infinitely often enabled, I should take it infinitely often. Does that rule out this behavior? Yes, it does, right? Good, because this is now not fair anymore, and therefore the property is satisfied. Good. One remark, maybe superfluous, maybe not. Suppose that one of these actions, A1, I mean, there is a difference between taking A to be, for instance, two actions, like let's say alpha beta, and you take A, or you take, let's say this, or maybe the other. This is not the same as writing down this. Of course, you know this, because syntactically they're already different, but also from a fairness point of view, they are different, right? Suppose I do unconditional fairness. Unconditional fairness with respect to this set means I should take some of those actions infinitely often, maybe only alpha. Fine. This says unconditional fair, I should take alpha infinitely often and I should take beta infinitely often. Yeah, so there is a difference between these two things. Good. A hard question is which type of fairness to impose. Fairness assumptions should be as weak as possible. That's a kind of a general rule of thumb, right? I already argued in the beginning there are different flavors of what is unfair. So it's not clear up front which behaviors to rule out and which ones not to rule out. Yeah, but a general assumption is that you try to rule out as a small set. I mean, the easiest way is to rule out everything. Yeah, but that's of course not our incentive. Yeah? So I would like to rule out just a small part of it. So here are the traffic lights again. I would like to have a property that says both lights are infinitely often green. We already have seen if you don't impose a fairness assumption, this is false. Yeah, because one of the lights may starve. What kind of fairness assumptions can you impose? Well, if A1 is a set of actions of light number 1, if A2 is the set of actions of light 2, then you may something do like this. No unconditional, no strong, but you have something like a weak fairness assumption. A weak fairness assumption for A1 and A2. What does that mean? It means whenever some action of process 1 is continuously enabled, and the same for the actions of process 2, then you should take some of these actions infinitely often. Yeah, so this, I hope, we'll see that we had an example where light 1 was starving, it was not doing anything. This is not possible anymore, because in all states you see there is a green transition. Well, not green, I mean, there is a transition of light 1, because I can move here with light 1, or I can move there with light 1. Here I can take a transition with light 1, there I can take a transition from my light 1. But you never take this, and therefore this then holds. The mutex with the fair arbiter, the second example I used, this was the example. We have seen that this was the entire transition system, the property, a liveness property, each waiting process eventually enters the critical section. We have seen this is violated, right? For instance, we can move here and then we can take this cycle. And that means that process 2 is waiting but never enter the critical section. So this is violated. Maybe you think this is not fair. It's not fair because maybe here enter 2 is enabled, there is enter 2 is enabled. So infinitely often process 2 would have had the possibility to enter the critical section, but we didn't. That's maybe not fair. The fairness assumption that we could impose is something like this. No unconditional and no strong fairness. So these are the empty sets. And weak is something like enter 1 and enter 2. So what would this mean? This would mean if enter 1 is infinitely often, continuously enabled, then you should take it infinitely often, and the same for enter 2. Do you then satisfy this property? The answer is no. Why not? Same reason as before. Enter 2 is enabled here, enter 2 is enabled there, but enter 2 is not enabled there. So weak fairness is not enough. Why did I start with the weak fairness assumption? The rule of thumb is try to rule out always the least number of executions. So I always start here. Yeah, because then I rule out only hopefully a few. So I always start by considering something which is weak fair. If that doesn't work, then I move to something which is strong fair. If that still doesn't work, apparently you have to rule out more. You have to be more severe. Then we go here. So apparently for this example, this weak condition is not sufficient because enter 2 is not enabled. Here is an example with this fair arbiter again, but now each waiting process eventually enters the critical section, same example as before, and what I now do is I can impose a strong fairness assumption rather than a weak fairness assumption, and I do this both for enter 1 and enter 2, and I hope you see that this solves the issue. Solves the issue in the sense that now the property is satisfied. Of course, you could also impose a stronger condition, but then you would rule out much too more. Yeah? So you always go from out to the bin. Yeah, question?
But wouldn't I still take one of the upper-outer cycles where one of the enter transitions is not even enabled?
Yeah, this only solves... Yeah, but this only says if enter 1 and enter 2 are both enabled infinitely often, then you should take enter 1 infinitely often and you should take enter 2 infinitely often. You referring maybe to this one? Yeah, but there you see that enter 2 is enabled infinitely often and I take it, but enter 1 is not, right? It's not enabled infinitely often. So premise is true, false implies everything.
Yeah, I'm just saying we wouldn't consider this.
Okay, but then you're maybe looking for another fairness assumption and maybe another property. For this property, it's okay to impose this fairness assumption.
Yeah,
That's what I'm saying.
if our condition is that every process enters its critical section, and this allows us to take this upper loop.
This is the process that the property says each waiting process eventually enters the critical section. In this cycle that you mentioned here, process 1 is never waiting, right? And if it's never waiting, false implies everything. So process 1 is happy. Maybe you are not because you have another property in mind, namely the property that process 1 should enter the critical section infinitely often. So if we consider this, yeah, then this doesn't work. Thanks for hinting at this. So for this property, this is not the right fairness assumption. Yeah. So indeed, well, I take this symmetric example as as I take before. This is the blue cycle over here. That does not, is an example of a behavior that shows that D is violated. So what we can do is actually I now label these actions by request and request. So along this cycle, process 1 requests to enter the critical section, then it enters, etc. Yeah. And then you see that here maybe rec2 is enabled. Here process 2 could also request to enter the critical section. It's not waiting, but it starts to wait. And now what I again try to do is I start again by trying to impose a weak as possible fairness assumption. So I look at a weak fairness assumption, and it needs to be symmetric for both. So I take rec1 and rec2 as two sets. Yeah. Good, so now the question is, now my claim is, this still satisfies E. Why? Well, it already satisfied E when I had an empty set here. Yeah, so that doesn't change. Why does it satisfy D now? Well, the argument was, as correctly identified, that this cycle is maybe not so nice for process 2 because it's never going to enter the critical section. Despite the fact that it could have requested here, it could have requested there, and it could have requested there. So it could have requested in every state of the cycle. So from some point on, continuously, process 2 says, give me the chance to request. And it never gets its thing. So that's not weak fair. And therefore I impose a weak fairness assumption, and that's sufficient here to show that this property holds. Okay? So I hope you see that you need the combination of those two to be both able to satisfy E and D. Good. The same for process fairness, for interleaving and so on. I skipped this because it's not so, it's basically the same. So I would like to start, or not to start, I would like to end by basically going to argue or going to show that fairness assumptions for safety properties are harmless. Harmless means they don't affect the validity of a safety property. So my aim is to show, you give me a transition system, we don't consider any fairness, and you give me a safety property. Suppose the safety property holds. Now I impose fairness assumptions, because I also consider some liveness properties. And now I want to reconsider my safety property. Did this change anything? And the answer is no. But I have to impose a small technical detail in order to make that work. So, and the detail is introduced by this example. It's a bit of a stupid example, but that's exactly what it is supposed to be. So here we have just two states, a blue and a yellow state, and one action alpha, or one transition here, and then there is a self loop. The label of the self loop is not so important. And I'm interested in infinitely often A. Now, it looks like a bit of a strange property. Of course, it's not infinitely often A, right? I mean, because I am in a state and then immediately I'm leaving it. So there's no way to get this, to make this true, right? So you could say, well, maybe I would like to have unconditional fairness on the action set alpha to impose this. Does that help? No, because it says that you need to do, you need to take alpha infinitely often, and that's not possible. There is no run where you can take alpha infinitely often. So the answer is yes, it's true, because there is no fair path. This fairness condition says you need to be unconditionally fair with respect to alpha. That tells you the only runs I'm considering are the ones that remain, and the ones that remain are the ones that are fair, and those that are fair take infinitely often alpha. Which behaviors does this transition system have that can do infinitely often alpha? None. Yeah? Good. And then this empty set of traces satisfies all properties, so in particular also infinitely often A. Good. We are going to call this not realizable, because you're imposing a kind of fairness assumption which this transition system can never fulfill. Yeah? In this initial state already it cannot fulfill this. So I'm going to make this precise, and then the crux will be that for realizable fairness assumptions, they are harmless for safety properties. So what is realizability? Intuitively, realizability requires that each initial finite path, so each path that starts in some initial state and which is finite, it can be extended to a fair path with respect to the fairness condition that I'm considering, which is F. So basically this means the following, intuitively speaking. Suppose for the sake of argument we only have one initial state. This is my transition system. This is the initial state. Now I can reach by some finite path some state. So maybe I go here, maybe I go there, maybe I go here. Yeah? Then realizable means For every state that I can reach, for instance, for this state, it should be possible that from here I have an infinite run starting in that state, which is fair with respect to the condition or to the assumptions I'm considering. And this must hold for all reachable states, so also for this one, also for that one. And if I can move somewhere here, somewhere down in this dark corner, even there this should hold. So also for this reachable state, because there is an initial finite path that goes here, from this one it must be possible to still continue in a fair way. Yeah, that is what realizability means, yeah? Intuitively speaking. And now we say a fairness assumption is realizable for a given transition system. This, of course, depends on the transition system I give you. Yeah? If for each reachable state there exists a path, infinite, path starting in that state, which is fair with respect to the condition, to the assumptions we are considering. This is not realizable. Why not? There is an initial path, namely the empty path, that brings you to the initial state, and from this state on there does not exist any fair path with respect to this fairness assumption. Okay? So this is not realizable. Good. So I give you this fairness assumption, this triple of actions, of sets of actions. We have unconditional fairness. This might not be realizable. This weak and strong fairness typically can be realizable, guaranteed by some kind of scheduler. So typically it's the unconditional fairness what is the hard part. And now I come to the result that says basically realizable fairness assumptions are not relevant for safety properties. Remember the diagram I started with? I said today we're going to start about fairness assumptions. They will be relevant for all the properties in this dashed area, but they will not be relevant for safety properties. What do I mean with not relevant? I have a transition system, it satisfies a safety property, I impose a fairness assumption, then the transition system under the fairness assumption still satisfies the safety property. So this is the theorem. If F is a fairness assumption which is realizable, that's the technical thing I was mentioning. Every reachable state, it needs to be possible that you can continue in a fair way. And you give me a safety property. Then if my transition system satisfies the safety property E without any fairness assumption, if and only if my transition system satisfies under Fe. So the validity of a safety property is not affected by any realizable fairness assumption. That's what this result tells you. Good. This result does not hold for non-realizable fairness assumptions, right? Because now you may ask, why do I impose this condition? And here is a counterexample. This is a two-state transition system, and now the only difference with the previous one is that I have this loop alpha. Suppose I have an unconditional fairness assumption that says alpha. That means on every run you should take alpha infinitely often. Is this, I hope you see this is not realizable. Why is it not realizable? We have to check for every reachable state, in particular the yellow one, that from this on you should be able to do a fair computation. Yeah, it's not possible here to do an infinitely, I mean, this label is not alpha, that's my assumption. But that you cannot do a behavior where you can infinitely often do an alpha. So this is not realizable. Now look at the invariant always A, so this is the example safety property. T, the original transition system does not satisfy E, right? Because I can jump to the yellow thing. But it satisfies under this fairness assumption because this behavior that moves to the yellow state is ruled out because I'm saying you need to do infinitely often an alpha, which you cannot do if you move to the yellow state. Yeah, so here you see an example of a non-realizable fairness assumption which affects the validity of a safety property. But the good news is for realizable, and that's really a kind of a mild restriction, safety properties are not affected by fairness assumptions. This brings me to the end of the lecture of today. I wish you a very nice weekend and hope to see you back on, Tuesday. Thanks.